All right, so hello everyone. I'm Sylvain Lebresne. I will talk about Apache Cassandra today. I'm a committer on Apache Cassandra, and in fact, my day job is to develop the Apache Cassandra project, and I work for a company called DataStax that let me do that. So what I want to talk about is to show you a few of the recent features that went in Cassandra, basically. Some of at least some of the important ones. Or does it work? It works. So very briefly, hopefully you've all heard of Cassandra, and Cassandra is a fully distributed database. A database that's been built to scale, and that in practice is massively scalable. So that's kind of it's an old graph that was done by Netflix to like see how writes were scaling when you add nodes. So that's on EC2. But anyway, the goal here is to show that it does scale fairly linearly in number of nodes. Which is a nice property to have. But it's also highly performant, because if you scale but you're very slow, it's still nice, but it's nice to have a base that's not too slow. So that's a graph for, and that's not a talk about benchmarks, let me be clear on that, but just a graph from a VLDB paper. VLDB is a database conferences that were benchmarking a number of databases. And the one line here is Cassandra, so well, on that graph it's definitely better than the other, but the point is to say that it's not a very slow database to start with, and it does scale, right? So it's a serious database. And the last, or maybe not the last one, but one of the very important property that we care about in Cassandra is the reliability and the availability, right? So it's a database that is built so that it's always run, and you will never have the database down unless you do something really, really wrong. And so that's a few tweets of users that had good experience with that, and there is other, but I mean it's used by a lot of people, and it's something that's been proven over and over again, right? But it's also a project that I think evolved fairly quickly, right? And so today I want to show you some of the fairly recent features. But before going on to those one, I want to just go back over the last few versions of Cassandra and one of the big features that went in, just to give you an idea of that evolution of Cassandra. And so 2 years and a half ago, actually, we released Cassandra 0.7, and 0.7 was kind of the first. Well, I consider that as the beginning of the usable Cassandra. Before that, you kind of, if you didn't read the source code, it was probably kind of hard to understand everything. I mean, it was the beginnings. And with 0.7, you started to have something that was really usable. And in 0.7, we added things like dynamic schema creation. What that means is that before 0.7, you wanted to add a table to your database. You had to take a node, shut it down, update the XML file with your new data definition, and then restart the node, right? So that's a distributed database, so you have more than one node. You had to do that on every node. You could do that in a rolling fashion, so that didn't mean that you had downtime, but nonetheless, it was fairly crappy, right? So we added a query that just, create table, basically, so you can create a table dynamically. And then we added things like expiring columns, so you can insert some column in the database, and you can set a TTL, and it will expire automatically when that TTL elapses, so that there's a number of use cases. And we added things like secondary indexes. So before that release, we didn't add secondary indexes, so we only had like primary indexes that were the one you declare with the table, but sometimes secondary indexes are pretty useful. So to be clear, in Cassandra, you may heard sometimes that secondary index can be slow, and they're not always useful. Sometimes you have to use other tricks because they can be slow for some use case, but they are sometimes really useful. So that was nice. And then 6 months later, we had a new kind of major version. So we had minor version between those, but we had a new major version. And that version added, well, it added distributed counters. So they're things that count stuff. They are useful to do real-time analytics kind of thing. And they have a number of downsides too, so you want to read the doc carefully if you want to use them. But as it happens, I did a presentation about them in Berlin Buzzwords 2 years ago, so I think the video is somewhere online if you want to know more about that. And then we also added something that is called CQR, the Cassandra query language. We added the first version there, and I'll skip to that quickly because I will talk about that more later. And then we added things like automatic mem table tuning. So in Cassandra, the mem table is where we actually buffer the insert before writing them to disk. And so that's one of the important structure in memory that Cassandra has. And before 07, you had to configure a number of settings for all of your table on when we need to flush those, how many operations you need to have seen. There was a number of settings, and they were pretty hard to guess right, in a way, or you had to do a lot of experimentation. And what was even worse, that if you were at a new table, you had to kind of recompute all of them because your machine has so many memory, and so if you are more table, then you have more mem tables, so you have to recompute those things. So we added a lot of automatism so that it's much easier to use now, and all of that is done with Cassandra. You just tell it how many memory you have, and it will make that works. And then in still more than 1 year and a half ago, we had Cassandra 1.0. So at that point, we kind of considered that Cassandra was used by a lot of people in production. So we decided it's probably time to, you know, have a 1.0 version, so that because people do use it in production, so it is ready for that. It doesn't mean it's the end of Cassandra, but it means that we've reached a milestone. And in 1.0, we had a few things like on this compression. So we compress now the SS table on disks. And we have something that we call leveled compaction. So compaction, when you write data, you buffer it in memory. And then Cassandra will flush those mem table. We call that a SS table, and you have a compaction, a background process that actually compact those files on disk regularly. And the way you compact impact performances in many ways. So we added a new compaction that had some good properties for some use cases. So anyway. And well, a year ago, we actually had Cassandra 1.1. And Cassandra 1.1 added something that I call row-level isolation. So we always add row-level atomicity in Cassandra in the sense that if you do insert into the same row, you were guaranteed that either all of the insert or none of them would be persisted, right? But we had an isolation is that you could have a race between a write and a read so that the reader can actually see a partial updates. And we've fixed that in 1.1. And then there's concurrent schema changes here. It's kind of a link to that one. In 07, we actually added a ways to dynamically create column family, but you weren't able until 1.1 to actually do the changes concurrently. Right? You had to be careful that only one operator were actually doing updates to the schema. And in fact, here, the changes part is important because in 1.1, you still cannot do concurrent table creation. You can do updates. So the table in Cassandra have a number of settings that you can change. You can do concurrent changes to those tables, but you cannot create them concurrently, and that's kind of a bug of 1.1 in a way, and that's fixed in 1.2. I'll have a quick word at the end. And then we did things like improve the support for mixing SSD and HDD. So some people want to put tables that are more often accessed or that have need for better latency and things like that on SSD, but still for cost reason keep some of the table on hard drive, on rotational hard drive. So we made that possible, and then some more self-tuning. So really, in 2.5 years, we went from something where you weren't able to actually create a table dynamically to going into fairly more specific features. And now what I want to talk about in more details is about Cassandra 1.1. So Cassandra 1.1 is the current stable version of Cassandra. It was released in January. And we're at like 1.2.5, the last version released. And that was a version that has quite a bit of fairly big feature for a major version Cassandra. And I want to talk about 4 of them. There is more. I will just quickly list them at the end. But the one I will talk about is the virtual node TQL3. I'll quickly talk about the native protocol and tracing because I think it's a nice feature, even though it's a fairly simple one. So the first one is virtual node. Before going into virtual node, let me recall the way that data distribution works in Cassandra. So you have a number of nodes, and you have to distribute data over those nodes. The way Cassandra does is this. We take a hash function. That's MD5, so you take the MD5 function. And you actually consider the domain of that hash function. There's like 2 to the power of 256 values. So anyway, you consider the domain of that, and you consider that in a ring. You make that wrap, and that's what we call a ring. The next step is that you actually pick value on that ring. So here, the separation here are value on the ring. And you pick one for each node. So node 1, for example, will have this value. That's what we call a token of the node. So every node in a Cassandra cluster are what we call a token. The token is a value on the hash domain that we've picked. And for node 1, that could be this one. For node 2, that could be this one. Node 3, et cetera, et cetera. And those tokens are actually creating data ranges, right? That is, it creates data ranges because there's ranges of data so that the hash of that data end up in this range here, right? So that's what we call data range. And well, that's how we actually do distribution. We say everything between a node token and the next token on the ring will end up in the node whose token it is. So that's node 1 token, so the A range will end up in node 1. Right? And then, well, the next one, B, will end up in node B because that's the node 2 token, and node C and D and E and F, right? But we also want to do replication. So every node will have more than one of those range. They will actually have, in that case, I have three range because I have a replication factor of 3, which is something you pick. And so in that case, where we do something fairly simple, we say node 1 has this A, and we'll just take the 2 previous ranges, and then we're done. We have 3 replica, all right? And we'll do the same for B. So B will be B, A, and F, and C will have C, B, and A, et cetera, right? So you can actually change that and make things a little bit more complicated on how you actually pick the remaining replica, but the basic principle is this one. Okay. Now, in 1.2, we introduced something called virtual node, and what that does in practice is just that instead of having 1 token for every node, we have more than 1 token for every node. And in fact, I think the default when you want to switch vnode, which, by the way, is optional, you don't have to switch to it, but if you want to switch your cluster to vnode, you can set multiple tokens per node, and the default, I think, if my memory is correct, is 128 tokens. So you don't want 2 or 3, you want a bigger number of tokens. But in a way, except for giving more token to each node, the rest of the algorithm is kind of the same. You have each node will have multiple tokens, so maybe node 1, and I think I don't exactly, there's too much stuff to follow it, but node 1 will have maybe this token, maybe 1 here, and maybe 1 here, and then every node will have tokens that way that are along the ring. And you will still have this property that the node 1 will have the range between one of his tokens, there can be more than one, but for each of his tokens, he will have the range that is between his token and whatever is the next token on the ring, right? So that way, you will have more smaller ranges, but those ranges will be more distributed over our hash ring. And you still do the replica thing. So if you have A on node 1, you will have P and O. I don't know if that's really my schema, but that's at least the principle. And so why do we do that? Well, the main reason we do that has to do with repairing nodes or adding new nodes, in fact, which is the same. That is, if you say you had 5 nodes, right, and you had a fifth one, or that could be maybe that fifth node was actually existing, but it actually died. I think that's what the schema depicts here. And when I say died, I mean rather like explode, right? The machine just exploded, so the hard drive doesn't exist anymore. You buy a new machine and you say, here, replace that node. So the data that were in that node need to be re-replicated because it has been lost, right? It hasn't been lost for the user because there is replica, but concretely we need to rebuild the node, right? And we have the same thing when you add a new node, except that on top of that you have to redistribute the data. But that's still the same thing. And when you actually rebuild the data, because you have a small number of ranges, because you only have 1 token for each range, so it really creates as many ranges that there is nodes in the cluster. It means that this node can actually pull data only from a small amount of nodes. In that case, 3. And I think that's not true because it could actually pick a range here, but it wouldn't be useful because it has only 3 ranges to pick, so it can pick them from only 3 nodes. And if you have a much bigger cluster with 100 nodes, that's still true. You want to rebuild the node, it can only pull data from 3 nodes. Now the problem is this: when you do that transfer here, all those nodes are serving data, are serving reads and writes. Your application is still running. All that is live. So you don't want that operation to actually cost too much to that node. You don't want to use too much I/O for that. So those links here, they won't necessarily going full speed. So you will throttle those streams because you just don't want to put too many load on those nodes, right? And even if you don't do it, you have a limitation for the cable, right? So if you have 100 gig of data to transfer here, it can take time, especially if you throttle, which is something you want to do often. So rebuilding a node will just take a long time just because you're using only 3 links, and those links are limited because you want to do it. So it's slow. Now, if you actually use virtual nodes, it gets much better because you have a lot more small ranges. And again, in practice, you will have a lot more ranges because you don't have like 3 tokens per node. You have like more than 100 ones. So you can actually pick tokens from pretty much all the nodes in the ring. All the node in the ring could be used to repair that node. And what that means is that you have much more of those links that you can use, and you will rebuild that node much faster without necessarily using too much resources on the node that actually are sending the data on that node. Note that this one will get much more data quickly, but we don't care because that's the one that's not yet doing real work. It's just rebuilding. It only has that to do, so you want this to be the fastest possible. And so that's why we want, that's one of the reasons we want virtual node, probably the most important one. And that's actually matters because when you rebuild a node, you may have a lot of data to transfer, and if you start having a bigger cluster, well, that can take a lot of time. So that does make a big difference in practice. That can make a big difference in practice. So that's virtual nodes, and for this presentation, I'll move to something else. But before that, so first thing is, let me just say very quickly that we call them virtual nodes in Cassandra, but there is something called virtual nodes in kind of the literature that's not exactly the same concept. Or we have a light version of virtual nodes. So if you have already heard of virtual nodes and you're like, that's not what they're doing, then that's kind of true, but we still call them that way. So really all this does is we assign multiple tokens per nodes and update the distribution algorithm for that. Now, the main pros of that approach is that you have faster rebuild, as I've discussed, but there is a few other perks, like it allows heterogeneous nodes. Because when I say that you have multiple tokens per node, you can actually have a different number of tokens for every node, right? So you can easily give more token to a node, and naturally, because you distribute your token evenly, you will have more load on one node, so you can have nodes of different capacity, basically. You could do that before with the token, but that was much more painful to actually do. And, well, the other one is like when you actually add nodes, it's simpler operationally with virtual nodes because you actually have less data to move around just because the way it works. So I don't have time to show you that in a schema, but you can take a paper and you will realize it's better. Anyway, so moving on to the other what I think is another fairly big feature of Cassandra 1.2, which is the Cassandra query language. And to be very clear, here I'm talking of the version 3 of the language. So I said earlier that in 0.8 we had the first version of CQL. And so we tried a little bit to get something that was working for Cassandra, and that takes some time. So we had version 1, we had version 2, and we're at version 3. And I strongly believe that it's the version that we wanted from the beginning. So I don't think we'll have a version 4 in the next release. I really don't believe we will. And that's what I will describe here. And it's fairly different from version 2, to be perfectly honest, right? So it's a relatively major revision, and in my opinion, a more ambitious one. So the goal of that Cassandra query language is really kind of to provide a simpler and a more abstracted interface to interact with Cassandra as a developer, right? Before that, we have, or we always have, and we continue to have the Swift interface, which is called the Swift interface because it used the Swift RPC framework. But that one it has a number of problems. It's hard to use. It's hard to make evolve with version. If you want to add new features, it's hard to make it evolve in a way that don't break the clients. And well, there was a number of reasons. And more importantly, it's not abstracted, right? So it exposed very directly how Cassandra works internally. So as a developer, you are exposed to a number of implementation details you shouldn't have to care about, right? And if you've used Cassandra for a number of years, you don't care anymore because you know all those quirks and that doesn't matter. But for new users, that's just painful. That's just a number of small things to understand and that don't necessarily make sense except from the fact that's the way the implementation works. And on the other side, it also means that because the API exposed very directly the way the internal storage engine works, it also means that it's a little bit harder to actually do a number of improvements to that storage engine because you may break the API that exposes irrelevant details. So anyway, that was kind of the motivation for that new API. And if you want a quick idea of what the Cassandra query language is, if I should describe it in 2 words, I would say that it's a denormalized SQL. So it looks like SQL if you read it, but it's still Cassandra. So when you use Cassandra, you actually denormalize data. You don't normalize like in general you do in SQL or in traditional relational database, but you will denormalize. And I'll give a quick example, right? So really, that's an SQL, but that's really what I call strictly real-time oriented. And by what I mean here is that we have no join, so it's not SQL at all. We don't do join. There is no syntax for joins. There is no subqueries. There is no aggregation. There is some order by, but it's limited. You can do arbitrary order by. So that's limited to what Cassandra does quickly, I would say. So I'll give 2 examples to give you a feel how it looks like. And my running example will be like storing songs and playlists. So say you're writing a music player or whatever, and you need to store songs in that. So, well, the way you do it is fairly, if you know SQL, which you probably do, it's fairly simple. You create a table that's called songs, and you will create, each song will have an ID. So the ID will be a UID, which is, so in Cassandra we use UID because that's an easy way to get a unique ID. without having centralization. So we don't use auto-increment ID, for example, because that's hard to do in a distributed store. So we use UID, but that's just a unique identifier for a song, and then you may have a title, some artist, some album, maybe a track number of that song in the album, and then in CQL we do support some collections. So we support sets, lists, and maps. So you can have tags that are, sets of text. Then you can insert a bunch of songs, and you'll have some data here that will look like that. So it's kind of boring because everyone understands what that means, but that's a good thing in our opinion. One remark, though, is that those two operations here, they are both upsert in CQL. So they are both update or insert. So really, the insert in CQL is like syntactic sugar for an update. We have both syntax because people are used to both syntax, so why not? But if you do an insert and the songs already exist, the database won't complain. You can still, in your code, choose to use insert wherever that's supposed to be insert and updates wherever that's supposed to be updates, but the database won't complain if you use it the wrong way. And that's due to a number of technical reasons. So that example was like fairly trivial and interesting. And the more interesting one is, what if I want to store playlists for a user? So for a user, I want to store a playlist that has a name and a number of songs. If I'm doing a relational database and traditional kind of SQL, I'll probably have a table that will be fairly simple. It may have a user ID, probably the playlist name, and then it will just have the song ID. And whenever I want to do a query like, well, give me the 51st songs of a given playlist for a user, I will just do a join, and that's it. And we don't do join in Cassandra. But instead, what we do is we denormalize. And so denormalizing is just saying that in that playlist, we just include, we just duplicate some data on the song in that table. Here, as you can see, I don't put all the property of the song because maybe I don't need them. And the trick here is that that table will depend a little bit on what your application do. So when you're modeling Cassandra, you start from the query, and then you decide how you actually model. So maybe here in that example, I've decided that I only care about those three values to do whatever I need to do with my playlist. And maybe the song ID, so that maybe I will only display that on the pages that show the playlist. And maybe if someone clicks on a song, then I will use the song ID, but that's another request to have the details of that song. Okay, so that can change, but that's the way it works. So the one thing, however, that's interesting in CQL and that changes from SQL is the primary key here. The primary key here has the same meaning that SQL. Those columns identify uniquely a row in that table. However, there is additional meaning in CQL3 for those values. And the additional meaning are those one. The first value in the primary key here is what we call the partition key. So when I say the first value, it can actually be, as in this case, multiple columns, but that is why I have the additional number of parentheses here, because the first element in the primary key will be the partition key for Cassandra, and I can group them with an additional set of parentheses, right? And the partition key is what determines on which node the row will go. So in another way to say it is that it's on those columns that the hash value that we use to do distribution will be computed, right? So what here that means is that all the songs for a given playlist of a given user will be in the same on the same host, right? So those two lines here are guaranteed to be on the same host, which in practice mean I can request them quickly because I know that I will only have to hit one machine and know the whole cluster. Even if in that playlist I have a lot of songs, here I have just 2 songs, which is a trivial example for, my slides are only that big. But if I have a lot of songs here, I'm still guaranteed they will be on the same host for a given playlist, which belongs to a given user in that case. And then the second part of the primary key, which is the rest of the columns here, they are taken together. They are doing what we call the clustering key in SQL. And that clustering key actually defines the ordering of the rows on disk. So as some of the SQL databases have some very similar notion of clustering. That's where the names come from. But in any case, in Cassandra, what that means is that here those two lines here will be in that order on disk because L is before M, right, basically. For a given playlist, all the songs will be alphabetically ordered by title. And if two of them have the same title, which usually don't happen, but that can happen, then the album will decide what is the actual sorting of those two rows. So that's what allows you to do efficient query in the order that's defined by the clustering key. So with that schema, you can do things. You can do very efficiently queries like, give me for a given playlist, give me all the title that are between B and C, for example. That can be done very efficiently because that will eat only one box and that will read pretty much a contiguous part of the hard drive. That's a little bit more complicated in practice, but that's still kind of the idea why it's efficient. And you can, of course, have the 50 last songs ordered by title, right? And so depending on the order that you need, you may need to change the way you actually store things, but then again, it's the way it works in Cassandra. And that's why I have for SQL3, it's a little bit short, but nonetheless, obviously give you a good feeling. Now, continuing with the features that we added in 1.2, along with the SQL3, we actually added what we call the native protocol, which is actually a binary transport protocol for SQL3. And so, as I said, the kind of legacy API for Cassandra is Swift because it used the Swift RPC framework. So the API is both some functions, some RPC calls, but Swift also handles the transport for us. So it does the transporting the query to the server and then transporting back the data to the client. But for SQL, we don't really need that anymore. So initially, in the first releases, we've reused the Swift transport for SQL. We've added just one code that's called execute. It takes a string, and it executes it server-side, and it sends back the data using Swift. But ultimately, we wanted to not depend on Swift for a number of reasons. But some of these reasons is that by doing a binary protocol ourselves, we can make it, we can optimize it for SQL3, and we can have some property that you cannot really easily have with Swift, like being completely asynchronous. So that one is not completely true for Swift, to be perfectly honest. But Swift is RPC-based, so the call to the Swift methods are blocking by design. So Swift is doing a number of tricks internally, so you don't have to have one connection for every thread if you want. But nonetheless, the API is kind of synchronous by default, and the native protocol is really asynchronous all the way. So you can have on the same connection, you can pipeline multiple queries on it, and you can have an API that uses that to expose a truly asynchronous API. And the other one that you actually, to my knowledge, cannot do with Thrift is that we have server notification with that node transport. So a client can register on the connection to receive some events. And to be perfectly clear, so far, the only events that we actually send are like cluster generic thing, like a new node was added. But that's still fairly useful because for clients library that you use, it means that whenever you start new nodes because you have new loads and you need more nodes in your cluster, then the clients themselves will be notified and they will add the new nodes to their pool of connection, and then you will use them in your queries and you will load balance better your queries and everything like that. And there's other events for schema changes, a few things like that. We don't yet have like user type, you cannot as a user register for notification, but at least having a protocol that allows it, we may allow it to one day. We don't know if we will, but we can fairly easily do it. So anyway, if you want to have a feel of how all that works, I encourage you to test the DataStax Java driver that's on GitHub. It's open source, and it's probably the more mature driver that uses this new protocol and CQL3. Now, the kind of last feature that I want to discuss for 1.2 is request tracing. It's a fairly simple thing. It's just that you can execute a query and just say, I want to trace that query. Okay. And here, that's what we do with CQL-fetch, and what it will give you is this. So the colors are mine. They just say that all this is what happened in one node, and the blue one is in another node. But what this tells you is that the first node actually received the query, and it actually sent it to the second node because the second node is probably a replica for that query, while the first one wasn't a replica for the query. And then the first one actually applied it, and it does a bunch of stuff, and then it sends back the answer. And you have the time for that, so it actually helps you see what's taking time in your query. And to illustrate how that's useful, I want to show you some anti-pair in Cassandra. So I will show you something that you shouldn't do in Cassandra, or you should probably not do it, at least not do it that way. But the first time you learn about Cassandra, you may be tempted to do it. And that's a message queue, right? So one way that would seem easy and fairly efficient to do message queue with Cassandra is to create that kind of table. You create a table queues, and you will have a number of queues that will be identified by an ID, so that's identifying my queue. And in the queue, I will have messages that they will be created at a given time. That's what identifies my message. I ignore the fact that I can have multiple messages on the same timestamp. It's easy to solve, but for my example, it's not relevant. And then you have a value of your message, whatever that means. So here, the partition key here would be the ID, which means all the elements of my queue would be on the same host. So I can query a queue fairly quickly, but I still distribute all my queue on my cluster. And then the clustering key is the created at, which pretty much guarantees that the queue is ordered by the event's time. So it's basically a queue. It's ordered by when the events was pushed. And the way I will make, so what that gives me is that if I insert new element, I use the current time here, and I will have things added at the end of the queue. And I want to process an element where I will read the head of the queue. I will process the element, and I will remove it, and I will continue. I will read the new head of the queue, process it, and erase it. So there is, of course, concurrency issue. If you do that naively, you may process twice the same message, but for number of use of queue, it's actually perfectly fine. So at least you're guaranteed that you will consume every message. So that looks fairly nice. And I said that the sorting here was guaranteeing somewhat efficient queries, so why shouldn't that be efficient? Well, if you actually use that queue a little bit, and then you trace the queries that actually grabbing the head of the queue, so here we're grabbing the one element of the queue, and I order by created at to have the smallest one, so the head of the queue. I'll get this trace, and the important one is the red one that I've highlighted for you here. But what it says is that it has read on the actual node that actually executed the query. It has read one live cell, and it's 100K tombstones. And tombstones in Cassandra is the way we deal with deletes. So for a number of technical reasons, when we delete Cassandra, we're actually inserting something that say that column is deleted. And we keep that tombstone for some times, right? We have to keep it for a few days, basically. Otherwise, we could have problems with resurrecting stuff and whatever. So anyway, so that's the way we deal with deletes. And because of that, when you actually delete elements that you have processed, those tombstones will be there for sometimes until they are actually reclaimed. So in practice, when you read the head of the queue, you have to skip all those deleted stuff that are actually still there before reaching one live cell, which is kind of the current head of the queue. And well, skipping all of that is going to be slow, so here there's a fair time bump here. And with tracing, you can very quickly understand what is going on. Of course, you do need a little bit of understanding of how Cassandra works, but at least that points you very clearly where the problem here is. And well, there is ways to make it better in Cassandra, being a little bit smarter, but that you shouldn't do it that way for that reason. So anyway, that concludes like the feature that I want to present in details, but in 1.2 we had a bunch more features, including things like, so that's the last part of the concurrent schema thing, which it's in 1.2 you can now create a schema table concurrently, right? Before you could only update them, and now you can create them. Then we improved the support for just a matter of disk. So Cassandra already do replication, so a lot of people don't want to use things like RAID 5. And even RAID 0 is nice, but if you want disk, you lose all of your disks. So it can be annoying because it's long to rebuild, and so it may not be worth it. So there's a number of users that actually use just a matter of disk. And before 1.2, the problem was that if a disk was failing, Cassandra was trying to read it all over and over again, and that was not very efficient. So we've fixed that. We've moved a number of structure off heap, so I won't go into details, but well, if you know Java, you know why we do that. And the last one that's worth noting maybe is we have a new partitioner, and here that's kind of the hash function I was talking about, and I said it was MD5. And that's true, except that in 1.2 for new cluster, you can use a new hash, which is based on Murmur 3, which is a faster hash, and that's good enough for the purpose of distributing data. So there is that. And so very, very quickly, in conclusion, I want to mention the next Cassandra release. So the next Cassandra release will be called Cassandra 2.0. It will be released in July. When, I don't know, but in July, hopefully. And what do we have for you in that release? Well, we have a number of stuff. We have a number of improvements to the CQL3 I showed, and more, and even more updates to the native protocol, actually, like things like paging query automatically. So that's something that we strive to do manually. It could be a little bit painful, and we've made that automatic with that new protocol. That's also something that the new protocol allows us to do. And one thing that's, that will be fairly handy is we've added a compare and swap operation. So in practice, in CQL3, it will look like that. You will be able to update a table, setting a number of columns and adding an if conditions here. That could be if not exist, if the row doesn't exist, or it could be if the column was previously some other value. So that's why it's really kind of a compare and swap. And we guarantee that this is executed atomically, right? And the way it works internally is use Paxos. And then we'll have some support for triggers. Don't really think about SQL trigger. You'll have to implement a class for now, but that trigger will be able to do something each time an insert is done on a table. It will be experimental, but you will be able to play with it. It's experimental because we know that it'll probably change some of the API that you have to implement with your trigger class, but you can start using them if you want to try it. And we'll have something called eager retries. And eager retries, the goal here is to have a better, like 99th percentile latency. And when in Cassandra you do a read, we're really always only asking one replica for the data. Even when you have like consistency level quorum or more, we're still only asking data on one node, and the other nodes actually send us like digests that are just there to check that we can fulfill the consistency level you ask. And the reason is to save network bandwidth. But the problem is that if you have a student event like a node dies and that was the one you just asked for data, then your operation will time out. It's not a huge deal in itself because the client will retry that operation, but in practice it's not very good for your latency. So the idea here, which actually comes from some Google presentation, but I don't remember which one, is just to retry, to send the first query, and if you don't hear back after a fairly short time, which could be based on your mean latency, for example, we'll query another replica. And maybe that's useless because maybe we'll hear back from the first query, but even if we do, in general, we won't retry every time, but still get a better latency. And that's all I have for you. No, yeah, we have performance improvement, but we always do that. So, and we have more. And thank you.